Hi, my name is Scott Simpson, and today we'll be talking about rate laws. So rate laws are an easy way to figure out the rate of a reaction or how long it will take to get a certain amount of product that you want, given a generic or any type of reaction. These have to be determined experimentally, and what we're going to do is we're going to talk about what are known as rate orders. So basically the exponents at which compound is raised in the rate law, how to determine that rate law, and then how to get the units on the rate constant associated with the rate law. So getting into it, let's say we have a generic reaction. We have a reaction little a with a stoichiometric coefficient of little a, molecule A reacting with stoichiometric coefficient B to B goes to C, capital C, D to capital D. And what we would like to do is we would like to determine an expression to get the rate of this reaction. So how quickly is this reaction going to proceed? To do that, every rate depends on its reactants, the production of its reactants. So our rate law will look something like this. Rate is equal to K, A raised to the power of X, B raised to the power of Y, and this is a lowercase k. So what these are the orders with respect to A and respect to B. So the important points are the rate only depends, in this reaction, since it's a forward reaction, only depends on the reactants. Another important point is the rate law must be experimentally determined. So you have to determine this from experiment. Rate law is determined empirically or from experiment. Okay, so now let's talk about the orders of a reaction. Order of reaction. So let's look at a simple rate law. Let's say we have the rate law. Rate is equal to K, NO2, or NO raised to the second, hydrogen raised to the power of 1. What we could say a couple things about this. The first thing we could say is with respect to NO, the order of the reaction with respect to NO is second order. We could say the same, something similar for hydrogen gas. The order of the reaction with respect to H2, in this case, is first order. Now, if we wanted to know the overall order of the reaction, that's where we add up all of these exponents. So 2 plus 1, third. So we get 3. The overall rate of reaction is third ordered overall. So when we're discussing the rate of the overall order, it's all of the individual orders added up. Okay, so now how do we determine these orders? This is what we determine experimentally. So how do we get this? So how to determine orders? So again, you have to have experimental data. But what you do is you do a series of experiments where you modify the concentration of one species at a time. So vary concentration of one reactant and look at the change in rate. So what we're going to do, we'll have trial number here. So we're going to have 3 trials, 1, 2, and 3. We're going to keep track of NO in terms of concentrations. So that'll be a molarity. We have 0.10, 0.10, 0.20 in trial number 3. Then we'll have the same thing for the concentration of H2 that's recorded in molarity, 0.10, 0.20, 0.10. And then we have our rate, or our initial rate, reported in molarity per second. That's usually what rates are reported in. 1.23 times 10 to the minus 3, 2.46 times 10 to the minus 3, and 4.92 times 10 to the minus 3. So we're going to ask the question, how would we determine the order with respect to NO? How would we determine the order with respect to NO? So we have to look at a situation where only the concentration of NO is changing and not H2, since those are our 2 reactants. So the only trial in which we're changing the concentration of NO and not H2 is trial 1 and trial 3. So experiments 1 and 3 are required. Basically, what we want to do is we want to set up a ratio. We want the rate of 3 divided by the rate of 1 is going to be equal to the concentration of NO of trial 3 divided by the NO concentration of NO of trial 1, all raised to a certain power. So let's look at that. So this is our expression for what we have. We can plug these things in because we have them up here in this table. So we have 4.92 times 10 to the minus 3 divided by 1.23 times 10 to the minus 3 is equal to 0.20 divided by 0.10, all raised to the power of x. As we start simplifying this, we find that this is 4 is equal to 2x. Now this is a pretty simple mathematical expression here. We easily know that the answer of x is 2, but let's say we get some decimals or something a little more complicated. How do we go through this mathematically? Well, this is where we start to use logs and the property of logs. So if we take log of 4, which is equal to log, so if we take both sides, 2x, the cool thing we can do is we can actually pull the x out front. So we get log of 4 is equal to x times log of 2. Now we can manipulate around, solve for x. We get log of 4 divided by log of 2, which results in a value of 2. So that means the order is second order with respect to NO. We knew that because we're using the previous example, but that's how you would find it. Let's do the same thing for hydrogen, H2. So what about H2? So we have that as a question. Again, we have to look back at our table. We have to determine, oops, wrong page, which one is changing, which one is not changing. So looking at these trials, we have to get a situation where H2 is changing and NO is not. So if we compare trial 2 to trial 1, that should work out okay. So in that case, we have rate of trial 2 over rate of trial 1 is equal to the concentration of H2 of trial 2 divided by the concentration of H2 for trial 1, all raised to the power of y. So we plug in our values. So we get 2.46 times 10 to the minus 3 divided by 1.23 times 10 to the minus 3 is equal to 0.20 divided by 0.10 raised to the power of y. And what this ends up working out to be is 2 is equal to 2x, or 2 raised to the power of x, which is easily solved for 1, but let's use our logs. Log of 2 over log of 2 equal to 1. Okay, so therefore, the rate law for this reaction is rate is equal to K, so that's our rate constant, times NO raised to the power of 2, H2 raised to the power of 1. And that's how you determine these coefficients. Okay. The next thing that we need to do is we have to determine what are the units on this rate constant. So question, what are the units of the rate constant? That K. This is going to depend on the rate or the rate law of whatever reaction we're considering. So in our case, we have rate is equal to K NO squared and H2 to the power of 1. Okay, we know our rate based upon our table. Our rate has to be in molarity per second. Our concentrations are in molarity. We want to try and find this value of K. So we have rate is molarity per second. We have our K value. We have molarity squared times molarity. Okay, let's combine like terms on this side. We get M divided by seconds, K times M raised to the power of 3. Now we want to isolate our K by itself. So K is equal to MS times M to the third. Reducing this, we get 1. I'm going to move the molarity out front. People just tend to do that. We get this as our expression, or molarity to the power of -2 seconds -1. So that's how you determine the units of the rate constant. So we've discussed what a rate law is, how to get that rate law, and how to find the units for this rate constant. With that, I'd like to leave you with any questions that you may have. Please feel free to contact me or leave a comment below. Thank you.